Hello, so today we are going to talk about central forces and central orbits, and also the main thing for today's class is we are going to derive the equation for the path of the particle under a central force. So let us just go ahead with the definition. You can see there on the board. A central force, it is a force which is always directed towards or away from a fixed point. The fixed point, it's called as the center of force. For example, the gravitational force. And a central orbit, it's defined as the path traversed by a particle under the action of a central force. Okay, for example, when you are having planets revolving around the sun, that orbit, okay, it is due to the gravitational force between the sun and the earth and also the other planets. So that orbit, it is the path traced by, suppose the planet is the earth, around the sun. Okay, so now I hope you understand about what is a central orbit. Okay, but the definition works for any kind of force which is a central force. So even if you are throwing a projectile under gravity, okay, when you are considering the force to be only gravity, then that is also the an example of a particle under a central force. Okay, so I hope it is clear. So what are we going to do? Now we are going to derive the equation of the path. Okay, if you remember that when we have to derive the path of a particle, okay, we can either use Cartesian coordinates, we can use polar coordinates, and we can also use intrinsic coordinates. Okay, so particularly in two dimensions, Cartesian coordinates can be described by xy, polar coordinates can be described by r and theta, and intrinsic coordinate can be described by s and psi. But over here, we are going to use polar coordinates. Firstly, we are going to use polar coordinates, and then we will also be discussing about something which is called as the pedal equation. Okay, so over here we are interested in these two, polar coordinates and pedal equation. All right, so let us just go ahead with it. Suppose a particle, okay, it's describing this curve, okay, and you have a fixed point over here which is called as the pole, if you remember, and okay, and this one is the initial line. Then what is happening here, suppose a particle is right here, then this position, it's described by two coordinates, that is the radius vector, which we call as r, and theta. Okay, so because a particle, suppose it is moving in this way, we know that the velocity will always be tangentially. Okay, the velocity will always be in this direction. Okay, but if you remember correctly, whenever we use polar coordinates, we are going to use radial and transverse accelerations. In case you had forgotten about what radial and transverse accelerations are, and if you want to be more familiar with them, you can refer to the link in the description. I have made another video about that. Okay, but just as a recap, okay, whenever we are using polar coordinates, since we are going to use radial direction and transverse directions, all velocities will have to be resolved along this direction, along the radius vector, which we call as the radial direction. And we are also going to resolve all forces, velocities along this line, okay, which is perpendicular to the radial direction, which we call as the transverse direction. Okay, so if you again refer to that video, you will see that the radial direction is given by the formula 1, and transverse direction, that acceleration, it's given by formula 2. Okay, so we can find the acceleration velocities in this direction. Okay, and then we are going to resolve. If we resolve the velocities, you will see that we will be getting only a velocity along the tangent. Okay, so briefly, that is what is happening with radial and transverse directions. Okay, now I am going to talk now something about number 3, which we are going to say it is the pedal equation. Okay, we know what is r, we know what is theta. Okay, but if you see relation 3, you have p. Okay, what is p? Okay, you are drawing this tangent. Okay, draw this tangent. Now from the pole, okay, we are going to draw a perpendicular. Okay, we are going to draw a perpendicular. Suppose this one is O, this one is P, this one is N. We are going to draw ON perpendicular to PN, then this one will be P. Okay, so since we are discussing about pedal equation, over here the pole, okay, it can also coincide with what we know as the pedal point. Okay, pole or pedal point. Okay, sometimes they may be different. Okay, the pole and the pedal point may be different, but in case they are the same, then they will satisfy the equation below. Okay, so P, it is the length of the perpendicular from the pole to the tangent. Okay, and you will also notice that we can even bring in intrinsic coordinates over here. We can even bring in this tangential angle psi. Okay, if this is psi, okay, so we can even bring this one here. All right. Okay, so with that being said, okay, about that relation number 3. Okay, in case you want to know how we derive that relation number 3, it's not important for what we are going to discuss, but we do need the relation. But in case you need the derivation for number 3, again, you can refer to the link in the description. There will be a PDF file, okay, which you can refer how to derive it. All right. Okay, so now what we are going to do, we are going to derive the differential equation. If you see the title over there, the differential equation of the path of a particle moving under a central force. Okay, so since we are having a central force, then there will also be something which we call as the central acceleration. Okay, and suppose the force, it's always directed towards this point. Okay, and the particle, it moves around, okay, just like the planets moving under gravity. Okay, so suppose it's moving in this way, and the force, it's always directed toward this point. And suppose, okay, the acceleration, it's F. Okay, and this one is the pole, which we will denote by O. Again, we will be having the initial line. All right. Okay, since firstly we are going to use radial and transverse directions, and then we are going to use the relation between r, p, and theta. So what exactly are we going to get? Okay, we will get these two equations. Okay, what we will derive is number one, this first relation, h squared u squared d2u d theta squared plus u. Okay, we are going to derive this relation where u equal 1 by r. And then what will we do next? We will derive another relation, f equal h squared by p cubed dp dr. This first relation, we are going to use only the radial and transverse accelerations. And for equation 2, because you notice that there is also this p, okay, so we are going to need the third relation as well. Okay, so let us just again complete that picture. So this one is p, okay, and this one it is the transverse direction, and this one it is the radial direction. Okay, solution. Okay, we are going to derive. So let a particle be moving under a central force where the acceleration directed towards the center of the force is F. And over here I should also state, sometimes the pole may be over here and the force it is directed like this, but sometimes what may happen is the pole may be somewhere else and the center of the force may be somewhere else. Over here the O and the pole, they are coinciding. Okay, so keep that in mind. Okay, if the pole and the center of the force they are not the same, then we will have to do some modifications. Okay, but this one we are deriving where pole and the center of the force O are the same. Let O be the center of force. Let P, let the pole also be at O. P r theta be the position at any instant of time. So what will we do next? We are going to use radial and transverse accelerations. Okay, so the radial, and also I should mention what is F. F, it is the acceleration provided by the force. And it's always directed towards O. Okay, sometimes it is towards or away. Okay, we are deriving it towards the pole. Okay, so now radial acceleration is equal to, if you see the relation, it is r double dot minus r theta dot square. Okay, but remember that this radial acceleration, it's always towards, so sorry, I made some mistake. This radial direction, it's always along the radius vector. Okay, so if you notice what I am drawing over here, then this acceleration provided by the force is F, which is in opposite direction to the radial direction. So over here we will be getting minus F equal r double dot minus r theta dot square. Let us name this one as equation 1. And also transverse acceleration, there is no transverse acceleration because the force is always providing an acceleration towards this side. Okay, so the transverse acceleration will be 0. If you take a look at formula 2, we will be having 1 by r d dt r squared theta dot is equal to 0. So this one will be relation 2. Okay, we don't need this figure anymore. So from relation 2, okay, we will be having d dt, we can multiply by r on both sides, r squared theta dot equal to 0. So d dt of something is 0, so which means that this one will be a constant. And this constant, we will denote it by h. Okay, right now we will just write it as h, but we will see after some time that this h will also have a meaning. Okay, maybe in the coming classes. Okay, and this h, it's what we are writing here. Okay, all right. So, and also u, it's equal to 1 by r. So from over here, we will be getting theta dot, it's equal to h u squared. Okay, but if you see what we want to derive, we have used this equation. We have used this equation to get this equation, which we will call as 3. Okay, maybe this one as 3 and this one as 4. We have used relation 2 to derive 3 and 4, but we have not used equation 1. Okay, so keep that in mind. We still have to use equation 1 at some point of time. Okay, but if you take a look at equation 1, we are going to need r double dot. Okay, we are going to need r double dot. Okay, so first, but r double dot, if we are going to find r double dot, we first need to find r dot. Okay, r dot, if you remember, it is dr dt. Whenever we differentiate with respect to time, we are writing it as r dot. Okay, r dot is equal to dr dt. So we can write this one as dr dt or dr d theta dt. And what will we be having? Dr d theta, we can write it as d d theta r, which is 1 by u. Okay, from over here, r equal 1 by u. D theta dt will be equal to theta dot. And over here, if you differentiate this one, you will be having minus 1 by u squared theta dot. Okay, so r dot, we will be having this much. Okay, so we will be having this. Okay, so sorry. Du d theta minus 1 by u squared du d theta dot. Or actually, okay, what we can do, okay, we can write down like this, d theta dt, okay, d theta dt, it will be equal to hu squared, okay, because it is theta dot. Okay, so I think it is best if we first write it down like this. Okay, dr d theta dot. Okay, so that you can see theta dot will be equal to hu squared. And dr d theta, okay, we are going to do what we just did, which is dr d theta 1 by u. Okay, this one, theta dot, it's equal to hu squared. We were using equation 4. Okay, so equation 4, also u equal 1 by r, it's near that. Okay, d theta 1 by u. If you differentiate, you will be getting minus 1 by u squared du d theta. So u square and u square will get cancelled. So you will be having that r dot will be equal to minus h du d theta. Okay, let us name this one as equation 5. We may or we may not require the equations, but it's always best that if we number them in case we do need them. Okay, now that we have found r dot, now let us find r double dot. R double dot, it will be d dt of r dot. But d dt r dot, it will be minus h. Minus h will be a constant, so we can take it outside. Du d theta. And you can write this one as minus h du d theta. Okay, we can rearrange the terms. D d theta, d dt. Du dt. Or we can even write this one as minus h d d theta. We can introduce another d d theta. And we can write over here d theta dt. Okay, so it's the same thing. We have just introduced some terms. Minus h. Okay, this one we can combine and we will be having d2u d theta square. And d theta dt will be again be theta dot. So ultimately what will we be getting? Again, theta dot, if you use equation 4, theta dot was equal to hu square. So over here we'll be getting minus h square u square d2u d theta square. So we have got equation 5. So this one will be equation 6. Next, what will we do? We will substitute it in equation 1. Hence from equation 1, equation 1 becomes, if you remember equation 1, it's minus f. Okay, I'll just write down again. So r double dot, we have got it to be minus h square u square d2u d theta square minus r. R, we can write it down as 1 by u. Okay, we can write it down as 1 by u. And theta dot will be hu square. Hu square, whole thing square. So this is what we will be getting. So we can cancel some terms. Okay, minus everywhere. Okay, so we can convert this one into a plus. And over here will become a plus h square u cube. So this is the equation that we want to find. That is f equal h square u square, we can take common, d2u d theta square plus u. So this is equation 7. Okay, one of the equations that we want to find. So if you notice that the force, it's equal to this one, and this one it is called as the equation of the path. Okay, which is the differential equation of the path in polar form. Okay, remember that u it's equal to 1 by r. Okay, so over here we have introduced so many notations. One of them is that u is equal to 1 by r, where u equal 1 by r. Okay, so we have got the differential equation of the path in polar form. Now we are going to derive it in pedal form. Okay, now if we are going to use in pedal form, If we are going to derive it in better form, we have to use relation 3. And over here, what we will do next, we will substitute r equal 1 by u. Okay, u equal 1 by r. So r will be equal to 1 by u. Substituted over here, we will be getting p, we will keep it as it is. 1 by r square will become u square, plus this one will become u power 4. And over here will become d theta r, which is 1 by u whole thing square. Okay, so now we will differentiate 1 by u. Okay, let's see how much we get. Okay, we will be getting dt theta 1 by u, it will be minus 1 by u square du d theta whole thing square. Okay, so after doing this, you will be left with this u4 and u square whole thing square will become u4, so you can cancel, minus square will become a plus, so ultimately it becomes a plus. You will be having this. Okay, but if you remember the equation that we want to get, is something that looks like this: h squared by p cubed dp dr. Okay, so there is still p, and also we will be needing r, and also it is a derivative with respect to r. So what we can do next is we will differentiate everything with respect to r. Okay, differentiating with respect to theta. Okay, you will see why. Okay, differentiating with respect to theta, we have, so if you differentiate this one with respect to theta, you will be seeing that we will be having okay, p power minus 1 by p power 3 okay, minus 2 upon p cube dp d theta. And if you differentiate this one with respect to theta, you will be having 2u du d theta. If you differentiate this one with respect to theta, you will be having 2 du d theta, and also you will be having d2u d theta square. Okay, so this is what we are having now. Okay, let us just simplify. The 2 we can cancel from everywhere. Next, what we can do is we can write minus 1 by p cube. Again, remember that we need that dp dr, so this is where we introduce it. We can write it as dp dr and dr d theta. Okay, and over here, if you notice, we can take common du d theta, so you will be having u d2u d theta square du d theta. Okay, we can take common du d theta. Again, what we will do, dp dr, we will keep it as it is. We no longer have to move. We no longer have to change it, because in the equation that we want to find, okay, I'll just write down so that you will see. H squared by p cube dp dr. Okay, in the equation that we want to find, dp dr will always be there. Okay, so we don't need to change it anymore. But this one we can still do something. Again, instead of r, we can write 1 by u, dt theta of 1 by u. And if you remember, okay, if you use equation, the last equation, okay, the differential equation in polar form, okay, I'll still write down this one as it is. Okay, I will change it after a few lines. du d theta, I will keep it as it is. Okay, you will see why. And this one, you will be having minus 1 by u squared du d theta. Okay, so we will be having this. Now, what is happening? You are having du d theta on both the sides, so we can cancel them. Okay, minus and minus will give you a plus. So you will be having 1 by u squared. Okay, or 1 by pq dp dr. Okay, u squared, we can take it to that side. Okay, so we'll be having this. But if you remember, that this one, it can be written as h squared. H squared. From the differential equation in polar form, we will be having that this one is equal to f by h squared u squared. Okay, using the differential equation in polar form. Okay, so we can cancel both of these. So ultimately, you will be having, therefore, f will be equal to h squared by p cubed dp dr. Okay, so this one you can conclude, which is the differential equation in pedal form. Which is the differential equation in pedal form. Okay, so these two equations, okay, you will have to remember them. Okay, we will do some problems later on, and these equations will be involved a lot. So to summarize, these are the 4 equations that you will have to remember. Okay, the 4 equations that you will have to remember. Okay, the first one is u equal 1 by r. That is very important. The second one is that theta dot, it's equal to h u squared. That is very important as well. The third equation that we want to remember is this: h squared u squared d2u d theta squared plus u. And the fourth equation, it's the one we just found, which is the pedal equation, h squared by p cubed dp dr. These 4 equations are very important. Okay, until next time.